Okay, so let's go on to the next topic. So remember what we were talking about previously? We were talking about subspaces, talked about the null space, the span. Okay, so the next topic is kind of an odd one. People generally find it a little bit abstract or hard to grasp. Linear independence. Linear independence. Okay. And I'm not sure if this is the right way to think about it, but one way of thinking about it is to think that our motivation is our goal. Our goal, in some sense, is to create a coordinate system for abstract vector spaces, for an abstract vector space. Okay, and it will become evident that what we need is some sort of minimal spanning set. Okay. Okay. So this term spanning set, does this make sense to you guys? What a spanning set is? Like you have some vector space. So I don't know. Right. Right. If you have V, a vector space, and W, a subspace, inside that vector space, then we call the set of vectors V1 through Vk, say, a spanning set of W. Spanning set of W if their span is W. If their span is W. Okay, so actually I think it makes sense to go back to the previous exercise. So recall the exercise we did at the end of class last time, which was in the previous exercise, we saw that this set 1, 0, 1, 1, 1, 0, 0, negative 1, 1 didn't span R. Right? Didn't span R3. Right. You remember this? This was the exercise we did at the last class. We said, is the span of this all of R3? And then it turned out that it wasn't. Right? The span wasn't all of R3. It turned out that, recall, if C minus A plus B was not 0, we could not get the vector ABC. Right? Remember that? I hope everybody remembers this. Right? We said, can you get an arbitrary vector ABC? And we saw that if this happened, then you couldn't get ABC. Right? Okay. Right. So what we saw was that as long as C minus A plus B equals 0, then we're okay. Right. As long as C minus A plus B was equal to 0, we're okay. But if C minus A plus B was non-zero, then we're not okay. Right. And so this thing here, the span was actually the plane z minus x plus y equals 0. Okay, right. As long as the z coordinate minus the x coordinate plus the y coordinate was equal to 0, then we were okay, right? So the span of this thing was actually this plane. Okay, the span of these three vectors was a plane. These three vectors were a spanning set for the plane. Okay, right, so right, these guys, where is it? Are a spanning set for z minus x plus y equals 0. Okay, everybody all right? Everybody all right with this story so far? Anybody confused? I can't read you at all. You're blank wall to me. Yes? No? Is everybody okay? Yeah. Anybody have questions? Okay. So let's look at the spanning set. Notice that if I add this guy plus this guy, what do I get? If I add the second vector and the third vector, what do I get?
0, 1. Second vector and third.
If I add this guy to this guy, what vector do I get? Well, I'm going to get
1,
0, 1. Yeah, 1, 0, 1. Yeah. I'll get 1, 0, 1, which is the first vector. Right? In other words, this guy is a linear combination of these two guys. Right? This one is already a linear combination of these guys. Okay. So in some sense, this guy is redundant, right? If I threw this guy out, then I'm not going to change the span, right? These three vectors span this plane, right? The linear combinations of these three vectors are this plane. But if I throw out this guy, do I change the set of linear combinations? No, right? So this one is basically redundant, right? This one is basically redundant. I don't need this guy. Okay, so right, this one is redundant. Somehow redundant. In the sense that throwing it out doesn't change the span. Okay. And so this is basically what we're going to be talking about. This is the minimality that I'm talking about. If I throw out one of these guys, do I change the span? Suppose I throw out one of these guys now. So I've already thrown out this guy, and I've got these two guys left. Okay. Suppose I throw out one of these guys. Do I change the span? Yeah, definitely, right? Because now you've got just a one vector. You've got multiples of one vector. It becomes a line. Okay. So I can't throw out these guys, right? So in some sense, these guys are the minimal spanning set. These guys are a minimal spanning set for this plane. Yeah, read.
So if you change one of the numbers in the first vector, will that, since it's no longer redundant with the other two, will that make it a span of 3D space?
Yeah, actually. Yeah. I mean, as long as you change it so that it's not in the span of these guys. Yeah, that's right. Okay, so this is sort of the idea of what's going to be going on. Okay, so let me sort of give another maybe simpler example. So suppose we're in R2. And we say, okay, we've got this vector and this vector. Right, so here's R2. We've got this vector and this vector, but we're also going to throw in this third vector. Okay. If I have these first two vectors, you see that everybody can be expressed at everybody can be given coordinates. You say like, this guy is one of the first guy plus one of the second guy, right? So this is 1, 0, say, and this is 0, 1. Okay. This vector here, you see, is 1, 1. In other words, one of the first guy and one of the second guy. Right. One of the first guy, one of the second guy. Okay. Right. If I'm talking about this guy here, then this is 2, 0. Right. This is 2 of the first guy plus 0 of the second guy. Right. 2 of the first guy and 0 of the second guy. Okay. If I throw in a third vector, then I have sort of too many ways of expressing, I have multiple ways of expressing the same thing. So for example, two zero vector is now expressible as, I could say it's two of the first two of, let's call these guys A, B, and C. Right? I could say this is 2A. I could call it 2A, but I could also call it like 3A plus negative 1C. Right? Okay. And so you see that I've got multiple ways of expressing this guy as a linear combination of the others. Okay. I've got multiple ways of expressing this guy as a linear combination of the others. Okay. At the same time, you see that this set has some redundancy to it, right? Because this vector, this guy, is already in the span of the other guys. Okay, the C is already in the span of A and B, right? The span of A and B is the whole plane already, right? Why did I throw in that C? It was actually useless. And you see that when I do throw in the C, I end up with this thing of, vectors being expressible in multiple ways. Okay. So I hope this is sort of motivating the definition that I'm about to introduce. So here is the crucial concept. So V1, dVn in V, a vector space. Okay. We say that the VI are linearly independent. If whenever C1 V1 plus C2 V2 plus Cn Vn equals the zero vector, we have that all the Ci must be zero. This is kind of a peculiar definition, but maybe one way to rephrase it is that the only way to get the zero vector, is the trivial way. The only way to get zero as a linear combination is the trivial way. Okay. So so think like this. If I've got a bunch of vectors and I say, let's look at the linear combinations of those vectors, can we get zero? Can we get zero? Okay, and you say, well, there's one way that always works. Okay? Just multiply everybody by zero and add those guys together, right? You take can you get zero as a linear combination? Sure, right? Just multiply everybody by zero and then add it all together, you get the zero vector, right? That's what I'm going to call the trivial way of getting zero. Okay, so linearly independent means that that's the only way to get the zero vector. That you have a bunch of vectors, and the only way you can get the zero vector is the trivial way. Okay. So, for example, let's look at these guys here, right? 1, 0, and 0, 1. How can I get the zero vector as a linear combination? How can I get the zero vector as a linear combination? Well, the only way is to multiply this guy by 0 and this guy by 0 and add them together, right? Because if A times 1, 0 plus B times 1, 0 is the zero vector, right? That tells me that A is 0 and that B is 0, right? A has to be 0, right? That would say that AB equals 0, 0. In other words, that A is 0 and that B is 0. Right? The only way to get the 0 vector as a linear combination of these guys is the trivial way. Okay, these guys are linearly independent. Okay, now look at these guys. Are there multiple ways of getting the 0 vector? Sure, right? Many ways, right? I could take one of this guy and one of this guy, right? I could take 2 of this guy and 2 of this guy. I could take, whatever. You take alpha of this guy and alpha of that guy, right? You add them together, you get the 0 vector, right? And that's a non-trivial way of getting the 0 vector. Okay, so these guys are linearly dependent. Okay, they're not linearly independent. So, right. So we say these guys are linearly independent if whatever blah blah blah. We have that all of the coefficients must be 0. Otherwise, we call the set linearly dependent. Linearly dependent. Okay. Coming back to our previous example, 101 here, right? Right. Are these guys linearly independent or linearly dependent?
All 3 of them?
Yeah, all 3 together. So are these 3 vectors a linearly independent set or a linearly dependent set?
Dependent?
They're dependent, right? Because if you add these guys together and subtract off this one, then you get 0, right? If you take, let's call them, U, V, and W, right? If you take negative U plus V plus W, you get the 0 vector, right? And so there's some non-trivial way of getting to the 0 vector. Okay? Okay. 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 A more abstract example. In P3, say, right, the polynomials of degree less than 3. Consider the set 1, 1 plus x, x, x squared. Okay, so you've got 4 vectors in your vector space, right? P3 is a vector space. You've got 4 vectors in your vector space. Are they dependent or independent? So think for 10 seconds. Turn to your neighbor and say, it's this. It's dependent? It's independent?
Because 1 x and
The answer is that they are dependent, right? They're dependent because I could say, I'm going to take 1 of the first guy, and minus 1 of the second guy, right? And I take 1 of the last guy, 1 of the third guy, and 0 of the last. And what I end up is with the function that's 0 everywhere, right? Each of these guys is a polynomial, right? I end up with this function that's 0 always, right? I end up with the zero polynomial, right? Right? I end up with a function that's 0 all the time, right? In other words, the zero vector of P3. Okay, so they're dependent. Right? Because you can find some combination that yields the zero vector. Okay. Okay. But if I threw out this guy, if I looked at 1x squared, right? I look at 1x squared, then that's going to be independent, right? There's no way I can get the 0 polynomial by combining these guys together, right? There's no way I can get the 0 polynomial by adding non-trivial multiples of 1x and x squared. Yeah, Avery.
Sorry, I just wanted to clarify for, like, when it says P3,
Yeah.
it's polynomials only of degree less than 3, so x cubed doesn't fall in that.
That's right, degree less than 3,
Okay.
not less than or equal to. Yeah, it's, maybe you'd like P3 to include cubics, but it actually doesn't.
Okay.
Yeah. Other questions? Yeah, Russ?
So if we can get a trivial way of the spanning set, does that mean we get like the minimum spanning set?
Right. So that's what we're going to see. That what you're seeing here is that dependence corresponds to a redundancy, right? And that independence corresponds to some sort of minimality, right? So dependence is basically some sort of redundancy, and independence is minimality, right? And so this is really how you want to think about what linear independence means. Okay, and it'll turn out that being linearly independent results in some its properties. Okay, so we're basically going to try to make this what this means clear. Okay. So here is an observation about dependence. So for a set to be linearly dependent, turns out to be equivalent to saying that one of the VI is a linear combination of the other. Of the others. One of the guys, at least one, it could be more, but just at least one of the VI is a linear combination of the others. Okay, so maybe we can call this a theorem. That linear dependence is the same thing as saying that one of the vectors is a linear combination of the others. In other words, is in the span of the others. Okay, so let's think about how this works. We're saying that a set of vectors is linearly dependent if and only if one of the vectors is in the span of the others. So to prove it, we need to go in both directions. Right? We need to prove if you're linearly dependent, then one guy's in the span of the others. If one guy's in the span of the others, then you're linearly dependent. Okay, so let's do the forwards direction. We say, okay, suppose that the VI are linearly dependent. Okay. Say, well, what does that mean? That means there exist numbers, C1 through Cn, such that C1v1 plus C2v2 plus Cnvn equals the zero vector. Right? And they're not all zero. Not all zero. That's what linearly dependent means, right? That there's some way of getting to the zero vector, some non-trivial way of getting to the zero vector. Okay. Okay. Well, why should that mean that one guy is in the span of the others? Why should that mean that one guy is in the span of the others? Yeah, Ian.
Doesn't you just subtract both sides by like one of the terms, like C1 V1, and then divide both sides by C1?
Yeah, exactly. Yeah, perfect. Right. So you say, well, look, let's say that C1 is non-zero. Okay. So we know that not all of them are zero. Let's suppose that the first one is non-zero. Okay. Then we can move that guy to the other side. We say, well, look, C2V2 plus CNVN equals negative C1V1. Right? But then, dividing both sides by negative C1, we get that V1. We get that V1 is a linear combination of the other guys. Okay, right. Now, it may be that it's not C1. Maybe it's one of the other numbers that's non-zero. But if it's one of the other numbers, you just do the same thing. Right. So, right. You know that one of these numbers is non-zero. Just do that. Just do that with that number. Okay. Right. In general, the way we argue at this point is we're usually saying we know one, right, at least one CI is not equal to 0. Without loss of generality, say it's C1. Okay. So let's just assume that C1 is the non-zero one. We can do that. If it's one of the other ones, just relabel them. Like call that one C1. Whatever one is non-zero, call that one C1. And then you see that that V1 is in the span of the other guys. Span of V2 through Vn. Okay. Okay. What about going backwards? What about going backwards? Well, if one guy is in the span of the others, you see how you just basically run this argument backwards, right? You say, well, if one guy's in the span of the others, then then just move this to the other side, and you've got a way of getting the zero vector, right? If you've got one guy in the span of the others, well, then you've got some way of getting the zero vector, some non-trivial way of getting the zero vector. So it's basically almost the same argument. Okay. Okay, any questions about that? Any questions about that? Okay. So see what this says, right? Linear dependence. Linear dependence means that one of the guys is in the span of the others. Okay. In other words, there's redundancy. Okay. Linear dependence means that nobody is in the span of the others. No one vector is in the span of the others. In other words, you've got the minimality. Okay, so this statement is really sort of codifying this this analogy here. Okay. 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 Another theorem. So another way of thinking about another point. Okay. So again, you've got some vectors in the vector space. Turns out that they are linearly independent if and only if, this is kind of a weird way of saying it, if and only if every vector in the span of those guys is uniquely expressible as a linear combination of the BIs. Say it again, right? These guys are linearly, what does it mean to be linearly independent? It means that everybody, if you look at the span of those vectors, if you look at the span of those vectors, you take anybody in the, wait, you guys are still copying. Yeah.
The V there, is it V1 comma?
Yeah, V1
Sorry.
comma. V1 through Vn. Yeah,
Does this imply like a perpendicularity between the vectors that are? I mean,
not exactly.
In some sense.
Yeah, not exactly. Right, because you could have something like this, right? And these two vectors, you know, there's no way of getting the zero vector. Right? So they don't have to be perpendicular, but it's something like they're not, they don't fall in line with the others. Well, I mean, it's exactly what we said before, right? That nobody is going to be in the span of other guys. Yeah. Okay. So this is saying, what does linearly independent mean? Linearly independent means that if you look at the span, everybody in the span is unique. Each vector in the span is uniquely expressible as a linear combination of the VIs. Okay. So what's the key part here? It's this word uniquely, right? It's the word uniquely, right? Because of course everybody in the span is expressible as a linear combination, right? If we say everybody in the span is expressible as a linear combination of the VIs, that's just the definition of the span. Right? Span is the collection of linear combinations, right? But the key word here is uniquely. Everybody in the span has only one way, there's only one way to get each person in the span. Okay. Okay. So let's see why this is true. So we're going to do the backwards direction first. Suppose you know that everybody in the span is uniquely expressible as a linear combination of the VIs, and you want to show that they're linearly independent. Okay. Does anybody see that this is this is actually very easy to say, easy to see. So linearly independent means that 0 is uniquely expressible, right? right? That the only way to get 0 is by multiplying everybody by 0, right? Well, if everybody is uniquely expressible as a linear combination of the VI's, then certainly 0 is uniquely expressible, and so you're done already, right? Right. So you say, well, look, if every vector in the span has a unique expression as a linear combination of the VI's, then 0 does. 0 certainly does too. 0 does too. Right. If everybody in the span has a unique expression, then 0 does, because 0 is in the span. Okay. And you say, well, 0 is 0v1 plus 0v2 plus blah, 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 0vn. So this must be the only expression yielding the 0 vector. Right? In other words, there's only one way to get the 0 vector, the trivial way. In other words, your set is linearly independent. Right? So the VI are independent. Okay. Does that make sense to people? Anybody confused by that? Okay, right. If we know that everybody is uniquely expressible, then certainly 0 is uniquely expressible. Well, here is one way of expressing 0, so this must be the unique expression, right? But that tells us that there's only one way to get the 0 vector, namely multiply everybody by 0 and add them together. Right? The only way of getting the 0 vector is the trivial way. Right? That's what linearly independent means. Okay. So going backwards is pretty straightforward. Okay. Going forwards is a little bit tricky. So I don't know if anybody's going to get it, but maybe somebody will. Okay. So you say, okay, let's suppose that the VI are linearly independent. Suppose these guys are linearly independent. Okay. We want to see that every vector has a unique expression. Every vector in the span has a unique expression. Okay. So you say, okay, well, but suppose there's, say V is in the span, you've got some vector in the span. And suppose that V can be written as C1v1 plus C2v2 plus CNvn, and V could also be written as D1v1 plus D2v2 plus DNvn. Okay, so you've got somebody in the span, and suppose you have two ways of getting it as a linear combination. Why must they be the same way? Why must the C's and the D's all be the same? The C1 must be equal to D1. We're hoping that happens, right? That there's only one way to do this. Russ?
You just subtract two equations.
Okay, so subtract. You say, in that case, 0, right? Subtract the lower one from the upper one, saying 0 equals C1 minus D1, V1 plus C2 minus D2, V2 plus dot 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 plus Cn minus Dn. Bn. Right? Right, and you see how this finishes up. You say, well, look, this is a way of getting the zero vector. Since they're linearly independent, all the coefficients must be zero, right? This must be zero, this must be zero, all the coefficients must be zero. By linear independence, Ci minus Di must be zero for all I. In other words, Ci and Di are the same for I going from one to n. Okay, so this is going to be really useful for us. It's this fact that if you have a linearly independent set, then everybody in the span has a unique expression associated with it. Okay, everybody in the span has a unique expression associated with it. Don't back up yet. I'm still going to say something. So, okay. So let me try to use the last minute to show you one last thing. So how does one check linear independence? How does one check linear independence? So here's an example from the book, right? They say are these vectors 2, 1, negative 2, 3, 2, negative 2, 2, 2, 0, 2, 2, 0, linearly independent? Are these guys linearly independent? Okay. That's the same question as asking, can we solve this system uniquely? Right? That's the same question, right? Can we get this? Can we right? Can we solve this system uniquely? Right? And so you see, the question is exactly the same question we've been dealing with all along, right? And the question is this matrix invertible? Right? In other words, is the matrix invertible? Okay. So linear independence is actually pretty closely related to the things we've been looking at all along. Okay. So we have a theorem, right? If the vectors A1 through AN are in Rn, and A is the matrix with these guys as the columns, then the AI are linearly independent if and only if A is invertible. In other words, a matrix is invertible if and only if its columns are a linearly independent set. Right? A matrix is invertible. Right? A is invertible if and only if the columns are linearly independent. Right? But remember that A is invertible if and only if A transpose is invertible. Right? But that means that the columns of A transpose are linearly independent. In other words, the rows of A are linearly independent. Okay? So we could also characterize this as the rows of A are linearly independent. Okay. So we're just sort of giving more ways of thinking about what independence means and what invertibility means. Okay, that's it for today.